Chapter 5 in Anton is about eigenvectors and eigenvalues. This word or prefix eigen comes from German, and apparently it means characteristic, proper, inherent, own. And David Hilbert, mathematician who lived in around 1900, introduced these. So here's the definition of an eigenvector and eigenvalue. So let A be a n by n matrix, so it's got to be a square matrix, so n rows, n columns, and a non-zero vector. So first of all, it's got to be non-zero. Vector in Rn is called an eigenvector if, when you take A, multiply it by x, you get a scalar multiple of x. So x is going to be called an eigenvector for A. And then the value lambda, that's called the eigenvalue. So here's an example. Let's take a simple 2 by 2 matrix, and let's check that this vector 1, 2, written here as a column vector, is an eigenvector for A. Now first you might ask, well, how did they come up with this eigenvector? And we'll show how in the next slide. But first let's just check it's an eigenvector. So we take our matrix A, our eigenvector, and do the matrix multiplication. 3 times 1, 0 times 2 is 3. 8 times 1, negative 1 times 2, add the result, you get 6. And that's 3 times the vector 1, 2. And so our eigenvalue is 3 for this specific eigenvector 1, 2. Now let's go back to the general case and see how to go about finding these eigenvectors and eigenvalues. So the general condition for an eigenvector x is that it satisfies A times x is equal to some scalar times x. And let's subtract off lambda x from both sides, and so we get this. And then let's write this lambda as lambda times the n by n identity matrix times this vector x. And that's to do this next step of factoring out an x. And so we have A minus this matrix here, which is just lambdas along the diagonals, times x equals 0. And we're saying that this equation here has a non-zero solution. So remember, the requirement that x was an eigenvector is that it's non-zero. Now we've seen that for a matrix equation like this to have a non-zero solution, that forces the determinant to equal 0. The reason again is if the determinant is non-zero, then we can invert this matrix and we conclude that x has to equal 0. But again, the condition to be an eigenvector is that it's non-zero. Okay, let's use this condition box to find out what the eigenvalues are, and from there we'll see how to find the eigenvectors in any particular case. So going to the example we just did of this 2 by 2 matrix, what we have to do is compute this matrix, compute its determinant, and set it equal to 0. So this matrix A minus lambda I2, so here's A, here's lambda times the 2 by 2 identity matrix. Remember, scalar multiplication of a scalar and a matrix involves multiplying each entry of the matrix by that scalar. So you've got lambda times 1, that's lambda. Lambda times 0, that stays 0, and so forth. Then subtraction of matrices is element-wise. So 3 minus lambda, it comes from here, 0 minus 0, 8 minus 0, negative 1 minus lambda is so. And then we want to take the determinant of the resulting matrix. That's denoted by these absolute value signs, if you will. The determinant is the product of the diagonals minus the product of the off diagonals in the 2 by 2 case. And so we get this, and then simplifying and doing the algebra, we get that the eigenvalues are 3 and negative 1. Let me explain quickly the code for how to do this in Sage. So here's our matrix, and then to find this polynomial determinant of a minus lambda I, well, actually Sage uses xi minus a. This polynomial I should have mentioned earlier is called a characteristic polynomial. Either one of these are called a characteristic polynomial. And so to get that, you do a dot and this method char poly. And so here's our characteristic polynomial. Note that it's very similar to the one here. Now 8 times 0 happened to become a 0. So, okay, and then we can further on factor it, and we get this, from which we can read off that the eigenvalues are 3 and -1. Or you could directly just ask Sage for the eigenvalues using a dot eigenvalues. Now let's find the eigenvectors associated with the two eigenvalues that we found, namely 3 and -1. So let's first deal with the case where the eigenvalue was 3. Then we need to find x such that a minus lambda I times x equals 0. So first let's find a minus lambda I. A minus lambda I is this matrix, and our value of lambda now is 3, so substituting in that, we get this is a minus lambda x. So we're trying to find x, and I've written that as x1 and x2 as its components, such that this matrix times x is equal to 0 vector. And then I'm going to row reduce, divide through by 8 to get this pivot 1, then move that row up as the first row, and so we've now got the row reduced form, and then we can see that x1 minus 1/2 x2 has to equal 0. x1 is a dependent variable and x2 is a free variable, so we've got x1 equals 1/2 x2 are the solutions for what x can be. And if I write them as a vector, x1 is 1/2 x2, x2 is the free variable, factoring in x2, I get 1/2 and 1, and so 1/2, 1 is a basis for the null space of a minus lambda I. In other words, 1/2, 1 is an eigenvector with eigenvalue 3. Now, any scalar multiple of this vector will also be an eigenvector. For example, 2 times 1/2, 1, namely 1, 2, is also an eigenvector. Similarly, proceeding in the other case, when our eigenvalue was -1, we get that the a minus lambda I matrix is now 4, 0, 8, 0. Then when we row reduce this, we get this matrix here, and then that tells us that x1 is the dependent variable, x2 is the free variable, and then x1 has to equal 0, x2 can be anything. So our choice of x is x2 times this vector here, and so 0, 1 is a basis for the eigenspace with eigenvalue -1. The definition of eigenspace is a space of eigenvectors of a minus lambda I. This is what this should say. And we can check that 0, 1 is indeed an eigenvector. Take our matrix A, multiply by 0, 1. This would just extract off the second column when you multiply by the second standard basis vector, and we get this result, which if you factor out a -1, which again was the eigenvalue, we get x. Here's how to do all this in Sage. So I've entered again our matrix, and the command is eigenvectors underscore right. This is because we're multiplying by x on the right of A. And so we're trying to find out what x should be when we're multiplying by x on the right. So when you type in just a eigenvectors, it gives a little bit of a mess. And so to read this, type in percentage sign, typeset mode equals true, and then trying the command again, it gives a little bit of a better picture of what's going on. But even here, this is a little bit cluttered. And what it is, is this is a list of 2 tuples. So let me extract off the first tuple. Remember, indexing starts at 0. So the first tuple of this list of two tuples is 3, then 1 comma 2, and then 1. Now what are these? So okay, the first number here is the eigenvalue 3, which we found, followed by the list of eigenvectors. In this case, there's only one eigenvector associated with this eigenvalue 3, up to scaling, and so that's 1, 2, which is what we had found. And then one thing we haven't explained is the algebraic multiplicity. That's the power of x minus 1 in the characteristic polynomial. But anyway, we can see that the eigenvalues are 3 and -1 as we found. The eigenvectors are 1, 2, that's the one associated to the eigenvalue of 3. And the vector, or the eigenvector 0, 1 is the eigenvector associated to the eigenvalue -1.